everybody. Hope you all are doing all right. This is a video over section 11.6, day 1. It's going to be separated into 2 parts, day 1 and day 2. So this is the first section that you don't have guided notes for. They are posted in the assignment. So if you are one of those people that like to copy down their guided notes, that is something you want to print off. But yeah, so this is the first one that I have not given you before break, obviously. Break, what am I talking about? Before this all happens. So go ahead and if you would like to, you can print those out. But again, that's not a necessity. That's just a if you'd like to. Okay, so we're jumping around a little bit. I know we just finished chapter 9, but we're jumping toward the end. We kind of thought of what do you need to know to go on. Talk about like bare bones of what you need to know. And we decided that the end of chapter 11 is really important. So we're jumping there. We're going to do 2 sections, then a quiz, and then we'll see where we're at, see how much we get through. Okay, so section 11.6, day 1. I'm going to get my, there we go. Okay, so section 11.6 is all about radical expressions. Okay, now we've worked with radicals before, especially when working with quadratics, because the inverse of an x squared is a square root. So we've worked a lot with them, but they were x squareds, which are quadratics. But now if we undo that, we take the square root of something. Okay, so an expression that contains any radical sign is called a radical expression. This is our radical sign, right? Get a pen here. Okay, there are many different types of radical expressions, but in this class, in Algebra 1, we're only going to study radical expressions that contain square roots, okay? So ones that could be reducible. And you know, when I talk about square roots, that implies that, you know, I could have like a third root or a fourth root of something or a fifth root of something. We're not going to talk about those. You'll actually get those in Algebra 2. Now, a square root is one where there should be like a little 2 written in there because it's a square root. Now, do we normally write those 2s? No, it's kind of like, you know, on a variable, we don't normally write the power of 1. It's there, but we don't actually write it. Same thing here. We don't normally write a 2 when in that little, you know, in that little crevice, what do you call that? That little indentation there is. Okay. Now, what's underneath the square root, what's inside the house, is called the radicand. Okay. So D is the radicand here. 2 is the radicand here. 18 is the radicand here. A radicand may contain numbers, may contain letters, may contain operations. Just depends. Okay. All right. So recall that the square root of 16 is 4, right? How do I know that? Well, because I want to figure out what number multiplies by itself to get 16. So 4 times 4 is 16. A lot of people think like a square root is like just dividing it by 2, and that's not the case. A square root is finding the number that it multiplies by itself to get that value, like 4 squared is 16. So 16 is considered what's called a perfect square. Now, you have these in your guided notes, but I want to talk through the square roots up to 10. Okay, and then we'll jump to bigger square roots in a second. All right. So here are some perfect squares. A perfect square is any number where if I take the square root, it's nice and even, nice and whole number. Okay. So 1 is considered a perfect square because that's 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 36, 49, 64, 81, and 100. You probably know those. Those numbers come up a lot. You probably know and have seen those before. Okay, ones that are not so readily available are ones that are from 11 to 20. Now, you know, back in the Stone Age when I was taking Algebra 1, my Algebra 1 teacher gave us a timed test on square roots up to 20. Do I still know them? Let's see. 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. That one's easy to remember because look, those numbers just kind of flip-flop. 15 squared is 225. 16 squared is 256, I believe. I'll have to check on that one. 17 squared is 289. 18 squared is 324. 19 squared, it's either 351 or 361. I'm going to go 361, and then 20 squared is 400. Okay, I've got to check a couple of those. I wanted to check 16 squared. 0. 16 times 16. 16 times 16. 356. Okay, I was right. 18 times 18. Did I get that one right? 320. Okay. 19 times 19. Okay, cool. So now, do you need to memorize these? Absolutely not. But what you're going to see here is these numbers come up very often. Okay. Now, when I ask for the simplest form of a square root, I'm asking for an expression containing square roots in simplest form when the radicand, thing underneath the house, right, has no perfect square factors other than 1. So you basically have to divide out any perfect square that's in here. Okay. The radicand has no fractions. You can't have a fraction inside here. And there are no square roots in any denominator. Right? Like if I had 1 over the square root of 2, no good. Right? That's no good. You can't have a square root in any denominator. So these are all ones that have not been simplified yet. Why not? Why is this one not simplified? Well, isn't 8 divisible by 4, and 4 is a perfect square? So I could take the square root of 8 and factor out a perfect square of 4. This is no good because there's a fraction inside there, and this is no good because there's a square root underneath in the denominator. Okay. Now, we're going to have to assume that we're only going to be working with positive roots here. Okay. Negative roots, we had that idea of having a plus or minus. We are only going to think about the positive version of them. Okay. Okay. It's sometimes called a principal root too. All right. So let's take a look here. I've got the square root of 2 over the square root of 50. Now, watch what I can do here. If I reduce down that fraction, I can have 1 over 25. 2/50 is 1/25. Now, what I can do is I can break that apart and say the square root of 1 over the square root of 25 and get 1/25. There's my answer. Okay. Now, let's keep it going. Okay, let's see what we got here. Well, 4 squared plus 3 squared. Well, that's 16 plus 9. Oh, okay. The square root of 25. What is the square root of 25? 5. And that's my answer. Okay, let's keep it rolling. Now, remember that this and this will cancel each other out. Right? So the square root of x plus 5 squared, those will cancel each other out, leaving us just with an x plus 5, and that's my answer. Okay, let's take a look here. Now, I'm going to teach you 2 different methods on simplifying these square roots. That's why there's 2 days of this. Today, what I'm going to teach you is called the factor tree method. Factor tree method. Okay. The next day's lesson, section 11, 6, day 2, is going to be removing square roots. Okay, removing the square roots, and I'll talk about what that means. Remove square roots. Okay, and I'll talk about what that means when I get there. Okay, so now, what is a factor tree? A factor tree is when it gets it down to its prime factorization. Okay, now here's how to make a factor tree. What we do is we make 2 branches, and we divide it down. Okay, so like 60 is 2 times 30, right? This is all multiplication here, factors, remember factors. 30, now we keep breaking it down until you get only prime numbers on the leaves, like here, 2. 2 is prime, so I'm done. Can't go anymore. 2 times 15 here, and 3 and 5 with my 15. So this factors all the way down to 2 times 2 times 3 times 5. I put all the leaves underneath the house. Now, I always call this the buddy system when I simplify square roots. So I want to buddy up any pairs that I see. The buddy gets to leave the house. Okay, so 2 square root of 2 gets to leave the house, and it leaves the house in a single. And now this 3 times 5, there's no buddies. There's no buddy of 3 and a buddy of 5, right? It has to have 2 buddies of the same thing. Like I can't buddy 3 and 5 out because they're not the same. Okay, so 3 and 5 have to stay in. They stay back together and multiply. 3 times 5 is 15. And there's my answer there. Okay. Let's take a look here. Square root of 72. Okay, so break that down. 2 and, you know what? You could do whatever you want. So a lot of times I do 2 and something else, but this is really, can I do 9 times 8? That's 72. And then 9 is not prime. I can make that a 3 and 3. 8 is not prime. I can make that a 2 and a 4, and then a 2 and a 2. So its prime factorization is, I've got 3 2s, 1, 2, 3, and then 2 3s. Okay, so that means my prime factorization is here and here. I've got 2 sets of buddies coming out. So I get a 2 coming out, a 3 coming out, and then a 2 is lonely on the inside. Now 2 times 3 is 6, and then the square root of 2. And that's my answer there. Okay. Let's take a look at 675. I'm going to have to break down 675. I see it's divisible by 5, so let's go there. 135. So this is a 5, and that's prime, and a 135. I see that that's still divisible by 5. Okay, so let's check that again. Let's divide that by 5 again. 27. 5 times 27. 27 is 3 times 9, and then 9 is 3 times 3. So this simplifies down into, we've got 3 3s and 2 5s. Okay. Buddy. So those come out. A 3 comes out, a 5 comes out, and then this 3 that has no buddy to come out with stays in. So 3 times 5 on the outside is 15. And that's my answer. Okay, let's keep it moving. One more out of that set. Yeah. All right, so let's take a look here. Square root of 96. Let's break that down. Don't worry about the 3 here. I'll address that in a second. We just break down the square root. 96. Let's take a look at 96. What's 96 divided by 2? 48. 2 times 48. And then 2 times 24. I like to just do 2s because that's really easy to divide by 2 when it's even. Because that's kind of like a, it always works if it's even. Right? It's just easy to do. Could I have broken this up like 48? 6 times 8? 48? Sure. This 24. Could I have broken that up into 3 and 8? Sure. You can still get the same prime factorization in the end. Now, this is where I'm going to carry through this 3. 3 stays on the outside. What's on the inside? Okay, I've got 1, 2, 3, 4, 5 2s. 1, 2, 3, 4, 5 2s, and then a 3. Buddy up. Okay. So on the outside, I've already got a 3. Leave that 3 on the outside times 2 sets of 2s coming out. What's left on the inside? A 2 and a 3. They go back together. They multiply back together to get a 6. Multiply all of these things here on the outside. 3 times 2 times 2 gets us a 12. Radical 6. And that's my answer. Okay. So what's the moral of the story here? The moral of the story is the 3 that was sitting on the outside stays multiplying on the outside to whatever comes out. Okay. All right, let's keep going. Now, radicands can have variables in them. Okay. Now, if I've got, let's kind of go through some variables. Okay. Now, x squared, isn't that just like saying x times x? Like that's its prime factorization if you just write it all the way out. So that comes out as just an x, square root of nothing, right? Okay, well this is square root of x times x times x. Okay, buddy system says again, oops, I didn't buddy actually. Oh, lost my sign lines here. So I buddy this up. So I've got one set of x's coming out, and then an x staying in. Okay, to the 4th. 1, 2, 3, 4. I've got 2 buddies coming out. So x and x coming out together to make x squared. X to the 5th. Okay. 1, 2, 3, 4, 5. Okay, so buddy that up. Buddies here and here. I've got 2 on the outside, making an x squared, and then 1 left over on the inside there. Now x to the 6th. 1, 2, 3, 4, 5, 6. Got my buddies here, here, and here. So 3 coming out, x times x times x is x to the 3rd. Okay. Now, what would happen if I did this craziness? Okay, so same rule applies, but now we just have 3 variables on the inside. So let's factor it all the way down. Right? We've got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3. Okay, let's buddy. Got 2 x's coming out. 4 y's coming out, and a z coming out. So this turns into 2 x's, 4 y's, and a z coming out. And then what's the only thing without a buddy? Oh, sad. Z. Got no buddy to come out with. Okay. So how does that apply to, reducing these radicals here with a number and a variable? Well, you basically do the same thing. You get it down to its prime factorization, and then you do the buddy system. So let's reduce down the number. 2 times 25. 5 times 5. That's its prime factorization. So this really reduces all the way down into 2 times 5 times 5, and then the prime factorization of the variables, x and x, y, y, y. Okay, so let's buddy up. Got a buddy of the 5s, an x coming out, and a y coming out. Okay, so a 5 comes out, an x comes out, a y comes out, and then what's left over on the inside? The 2 and the y left over on the inside. And that's my answer. Okay. Let's keep it going. Okay, so 160. Okay, that's an easy one to reduce down. 2 and 80, 2 and 40, 2 and 20, 2 and 10, 2 and 5. So this is, I got 1, 2, 3, 4, 5 2s. 1, 2, 4, 5 2s, and a 5. And then I've got 4 A's, 1, 2, 3, 4, and then 2 B's. Okay, let's buddy up. 1, 2, 1, 2, 1. Okay, so I've got 2 sets of 2's coming out. Well, I can just make that a 4 on the outside. 2 times 2 is 4. And then I've got 2 sets of A's, so it makes an A squared. And then I've got a B on the outside coming. Now what's left over? I've got a 2 and a 5 here to make a 10. Remember, those multiply back together. Don't add them together. That's not a 7. That's a 2 and a 5 to make a 10. And all the variables came out, so there's my answer. Okay. One more problem here. Okay, now this 5 sitting on the outside, leave it on the outside. Okay, now let's reduce down our 504. 504 divided by 2 gives me 252. 2 times 252, and then divide by 2, 126. 2 and 126, and then that should be 60. Oops, 2 and 63. 2 and 63, and then I know that 63 is 7 times 9, so I'm going to jump to 7 times 9, and then 9 is 3 and 3. Okay, so this is, I've got 3 2's, 1, 2, 3. I've got 2 3's, 1, 2, and then a 7. I've got 2 x's, and then 1 y. Okay, buddy system here, here, and here, and here. So that means the 5 is already out there. Don't leave the 5. 5 times 2 times 3, and then an x also coming out. What stays in? A 2 and a 7 get me back to 14, and then a y. So all in total, 5 times 2 is 10, times 3 is 30. And then I've got an x and then a 14y on the inside. That's a y, right? Okay, so the homework is a worksheet 11.6. Again, you don't have to print it out, but if you'd like to, you can. Make sure you get a good scan and send that in to me. Okay, see everybody.